We have seen in our previous lecture that study of oscillatory motion, or what we call commonly vibration of mechanical systems, is very important, primarily because the characteristics or the behavior or the response of a system to dynamic loading can be very different from that when the loading is static. So, a successful design will require a thorough study of the system from oscillation point of view or vibration of the system, what is being designed. We have also seen that the vibrations can be of various types depending on various parameters. So, what we propose to do now, we propose to start the detailed analysis of vibrations of mechanical or similar systems. And to begin with, we take up the simplest of all, that is the free oscillation of simple single degree freedom systems. Now, here again, before we start the detailed modeling and analysis, let us see that there can be different types of systems. And based on the nature of restoration, that is what brings it back to its equilibrium or other stable equilibrium position, can be divided into two groups. One is one type of system where the restoration is through elastic members or springs. The other can be field restoration, which means that there is no elastic member or there is no strain energy stored in the system which brings it back to the original equilibrium position, but it is a field which acts on the mass or the inertia that is responsible for restoration. And the most common type of field what we encounter every day is the gravity. Other is others, electromagnetic fields, electrostatic fields, magnetic fields, which we need not go into details. In both cases, you will find that the oscillation can be again classified into two groups based on the geometric nature of motion. That is linear motion, which means that the mass moves in a straight line, or angular motion. Same may be the case here. So, what we will do, we will see the popularly encountered systems of these types. Say this one example could be a cantilever thin beam carrying a mass at its end, or a parametrically lumped parametric model of a system. In this case, the mass is moving like this. In this case, in both the cases, the motion is rectilinear. In case of angular motion, is something like that: a disc mounted at the end of a shaft, other end of the shaft being rigidly mounted, or simply model we can have is a torsional spring and an inertia. Here of course we know that the oscillation will be angular. Same thing here, the oscillation will be angular. So here if it is represented by x, we will represent it by theta. In this case, the inertial property is represented by mass. Here the inertial property is represented by moment of inertia. The stiffness in this case is represented by K, which gives force per unit deformation. Here the stiffness will be represented by capital K, which will be torque per unit angle of rotation. So here again you will find, if you take for example a tube, here there is some kind of a fluid. So if we depress the fluid level little bit, we will find that then it will oscillate after we leave it. The example of this is the linear motion which is gravity restored. The angular motion which is gravity restored is very commonly known and almost everyone is familiar with that. That here the motion is angular. There are other types of gravity restored systems which can be considered to be, suppose if you take a half cylinder lying on a rough horizontal plane. If you disturb from this equilibrium position, we know that it will rock. So these are the elasticity restored systems, these are the gravity restored systems. There are many other examples which we did not consider now. Solving these problems, let us first take up one approach which is familiar to all of us, that is the Newtonian approach, that is Newtonian mechanics approach. Which mean that we will use this relationship force is equal to mass into acceleration or torque is equal to moment of inertia into angular acceleration. Both are the commonly known forms of Newton's laws, and we will use these laws and try to solve these problems. So what we will do, we will try to find out first the basic equations of motion. So this one. Now one thing we have to keep in mind, that we have to consider the system to be in stable equilibrium. So this is the simplest possible system we have taken up. And as mentioned that this is the equilibrium position. What does it mean? Means that if left alone, it will remain in this position. If you disturb little bit, it will try to come back to this position because this spring is there. And therefore, obviously, under this situation, total force acting on this mass will be 0. That is, in this particular case, that the spring force will be 0 in the horizontal direction, which means that this spring is at natural length. Now, we displace it little bit. Say we displace it here. The first thing is that how do we measure the displacement? Now, almost as a rule, unless otherwise there is a very special reason to do so, we should always measure the displacement or change of position from the equilibrium position of the system. So, therefore, if this be the equilibrium position, then the displacement will be this much. There will be only now vertical direction, the reaction by the ground and the weight is continuously balancing each other, because we are now interested only in the horizontal motion. And here the only horizontal force which is acting on the system is the spring force. The spring force is given by the stiffness into its elongation from its natural length, which is nothing but x. So, the acceleration of this algebraically is in this direction, and the Newton's law says that mass into its acceleration must be equal to force in this direction. How much is the force in that direction? It is minus kx. Minus because the force is actually in the negative direction. So, the basic equation what we get is x2 dot plus omega n square x equal to 0, where of course in this case omega n square is a. If we take up the other system, say this one, here the moment of inertia is I and stiffness of this spring is capital K, torsional stiffness, and this is the equilibrium position. So, when it rotates, suppose we measure the displacement in this direction from here, and this is the equilibrium position. So, then when the angular displacement is theta, as the torsional spring is now deformed, it will apply a moment in this direction, which is m. And the equation of motion, that means I, moment of inertia, into angular acceleration, that is theta 2 dot, must be equal to total moment acting in that direction, which is nothing but minus. So, here again we find the basic equation is theta 2 plus omega n square theta equal to 0, where omega n square is equal to capital K by I. So, the form of equation for both the cases is exactly the same. Let us consider the angular case. So, we will do only one, that is the pendulum, others we will take up later. So here the equilibrium position obviously is this is the equilibrium position. And we have displaced it, say, by an angle theta in this direction. So when you take this mass, the force acting on this will be gravity and a tension in this direction. That is the hinge. Now what will be the equation of motion for this? We can do two ways. We can find out the total moment of the external forces about this point O, and that we can then apply this moment of inertia of the system about this into theta 2 dot must be equal to the total moment acting in that direction. So that will, what is the moment of inertia about this point? It will be m L square, and the angular acceleration in the algebraically positive direction is this. This must be therefore equal to the total torque acting in this direction, and total torque about this point is actually clockwise, that means in the opposite direction, and it is equal to minus mg sin theta into L. Mg sin theta is nothing but the component of this in the normal direction, and this angle being theta, it is this angle being theta, this is mg sin theta. And this into the arm length is L, is the total moment acting in this direction, and putting a negative is because it is minus. So here again we get the equation in the basic form . So we find something interesting here, that the forms are somewhat different, and moreover this is a nonlinear equation. However, for small oscillation, which is always the case unless otherwise mentioned, we can write sin theta is approximately equal to theta, and theta 2 dot plus g by L theta equal to 0, or theta 2 dot plus so we find in gravity based system also the basic equation is of the same form. Let us take up another case where the equilibrium is not in the undeformed condition of the spring. What happens in such cases? We are discussing this particular situation where a system is at its equilibrium position, but corresponding to that position the elastic members are already deformed. Now such a system comes quite often, and in many cases there is confusion that whether the gravity force should be taken into account or not. That is why I am separately discussing it to remove any confusion which may otherwise may be created. Let us take a simple spring mass system, but now it is suspended rather than being put on a horizontal table. It is now suspended. What will happen next if we suspend this? The spring will stretch little bit and the mass will come here, because due to gravity there will be a force acting on this spring, and the spring will be stretched. So, the equilibrium position, this is the position which corresponds to undefined spring length, but this is the equilibrium position when it gets deformed by, say, an amount delta. Now, what is the equilibrium situation? What does it signify? That the total vertical force on this mass one is the weight, which is mg, and other is the spring force, which is k into the deformation of the spring, that is delta. And of course, since it is in equilibrium, mg must be equal to k delta. We measure the displacement always from the equilibrium position. Now finally, we give some further deformation or displacement to the mass from its equilibrium position. So therefore, if this is the equilibrium position, as mentioned before, we should measure displacement from this position. So this is the instantaneous position, and therefore this must be equal to x, which is measured from the equilibrium position. And now let us see what is the total force acting on this. One is, of course, the gravity, and other is, of course, the spring force, which is k into delta plus x, because now the total deformation from its undeformed condition or position is that means delta plus x. So now the equilibrium in this direction will be now m x2 dot is the total force acceleration of the body into the mass in this direction, and that must be equal to total force in this positive x direction, that is mg minus this. Or when you expand, now this, as you can see, this is equal to 0 from this. So therefore finally we again get back the same form of equation So this is a very important point we should always keep in mind, that even if the system is under equilibrium under the action of the gravitational field, and we measure the displacement of the configuration or the mass from its equilibrium position, there is no need to account for the gravity at a later stage. the gravitational pull, which was already balanced by the spring force while it was in its equilibrium position, is always there and getting nullified by each other. So therefore, when we write down the equation of motion, there is no need to put this. What we could do, we could just simply ignore that the existence of gravity. We will consider the case that there is only the displacement of the spring from its equilibrium position of the mass, which is kx, and we will not consider that the total displacement or stretch is delta plus x, so it will be k into delta plus x. So we can forget about gravity, everything, and that way we should get the correct solution. So this is discussed in great details because this is a source of problem and difficulty to many students. Now let us come to the question of solving, because we find that for all the single degree freedom systems, in some form or other, we get the same equation of motion. So therefore, we will now solve this equation. So the equation is same. So therefore, we have to find out the solution. Equation which we will solve is of this form. And you have all solved this equation, which is a very standard one, and we know that the solution is a harmonic function of time. And you all know that A and B are constants, and these constants are determined from the initial condition. So the values of the position and velocity at t is equal to 0, they have to be specified, otherwise the problem is not completely stated, and once they are given, we can find out the values of A and B. So how do we do it? We find out x dot t is equal to so at t is equal to 0, x equal to 0. If we put t is equal to 0 here, so this goes out, only this b remains. So that tells us that b is equal to 0. Similarly, at t is equal to 0, x is equal to x dot 0. We cannot say both are 0. So then what happens? We get, we substitute t is equal to 0, so omega n A is equal to x0 dot. So we get omega n A is equal to, so that gives us A equal to so the form of the solution in this case will be if we do the other way, that we give initially some velocity, some displacement but no velocity, then what happens? And at t is equal to 0, x dot equal to 0. Now, if x dot is equal to 0, if we put t is equal to 0, what remains? Omega n a. Now, omega n a equal to 0, that means a equal to 0. If a is equal to 0, then if we put t is equal to 0, this goes and only b remains. B is equal to so the solution in that case will be so depending on the initial condition we can have the solution. The general case will be and solution to this is quite straightforward. You can solve it. That means we will get at t is equal to 0, x is equal to x0. So, b is equal to x0. So, this is 0, only b remains and that is x0. Similarly, this will give from this is 0, this is omega n a, a is equal to and the solution is finally this will be the most general solution. However, we can express the solution with two constants as a and b to be determined from the initial condition in another way. Say if we take the solution and let us substitute a by square root of a square plus b square is equal to say then what we can get xt is equal to, now we can first multiply by square root of a square plus b square and divide this by a square plus b square, divide this by square root of a square plus b square, which are nothing but cosine phi and sine phi. So, therefore, it becomes sine and we can write this quantity as one quantity x, capital X, here of course we know that x is nothing but and tan phi we could do it other way also, all kinds of things are possible. We could write a by square root of a square plus b square is equal to sine psi, for example. then xt will be equal to x cosine where x is same and tan psi So, getting sine, cosine or such combinations, they are basically the same thing as we can guess. They are all simple harmonic functions of time. So, generally we can write the solution in any form and start from there. So, therefore, we can write the solution in this form or any of these forms can be used. They are virtually the same thing. I think once we get this, therefore we find our solution in graphical form will look like this. If we plot x versus t, if it is a sine function simply, then obviously that means when we get it, already we have seen it, that this is the situation when x0 is equal to 0, x dot 0 is equal to x dot. So, this is, that means you start it without any initial displacement, but by a velocity. Similarly, we can have, it is possible to have the solution like this. Where x will be x, and this is the case we get when we initially start with some displacement but no velocity, then we get a cosine function. And if both are present, that means initially we have given some displacement and velocity both, this is the case. So, therefore, what we find that it is a harmonic, the solution to this is a simple harmonic function of time, either sine, cosine or a combination of that, where the circular frequency in radian per second this is the natural circular frequency. The actual frequency in cycles per unit time. Now, to complete one cycle, the omega or the angle of the angular displacement of the vector representing this will be 2 pi. That means from here to here, we will find that it requires 2 pi radians for each cycle. So, if there are so many radians per second, so the number of cycles per second, which we call as half, is omega n by 2 pi. Now, if you want to find out the time period, that means what is the duration of this one cycle. The time period will be then obviously that if 2 pi is the angle to cover one cycle and omega n be the speed at which it is covering angle. So, obviously, this will be the time period. So, these are the quantities. So, therefore, we have found a very important thing that all single degree freedom systems without any damping, if disturbed from the equilibrium position, executes oscillatory motion where the displacement for small oscillation can be represented by a simple harmonic function of time, and it vibrates with a particular frequency and time period, which is a characteristic of that particular system, and its value depends on the parameters. We will solve problems to find out that how this omega n or fn or t are found out, that we will solve some problems. The importance of this study is one thing to be kept in mind, that you have noticed that not the determination of x, it is not a system property. It will depend on how much displacement you initially gave, how much energy you have put into it or to the system to initiate vibration. On the other hand, this frequency with which it is oscillating, that is a property of the system. And our general objective of studying free vibration problems of system is to find out this natural frequency of the system. We will see in the subsequent lectures why it is so important for us to know the natural frequency of a system which perhaps we are designing. That we will see later, but it will be enough for the present to know that determination of the natural frequency of a system is a very important task for designers. Now, I think before taking up some other thing, at this stage it will be desirable to have some discussion on the representation of harmonic quantities or harmonic functions of time by rotating vectors. We will make use of this in subsequent lectures. That is why we are discussing it, so that at a later stage we do not go astray from our main stream of discussion and take up this, which is not exactly related to vibration. Say here we want to represent a harmonic function of time, say graphically. A very convenient way of doing it is, if you take a vector, say A, and it is rotating with an angular speed, constant angular speed omega. And say we have taken or we have started measuring time at this line. So, this line represents t is equal to 0. If that be the case, how much is this angle? Omega n into t, because when it was here time was 0, the amount of angle it has traversed will be nothing but the speed, angular speed, and the time. Now, let us find out the projection. If you take this projection, how much is this? This is obviously A cosine omega t, and sorry, there is no omega n. And the y component at this instant is now, as it keeps on rotating, you will find this component y component will vary as a sine function of time, and the x component will vary as a cosine component, cosine function of time. So, the same thing you can do in a more general way. So, let us consider that so this be the vector of magnitude A and rotating at a constant angular speed of omega. And let us also pick up this position which corresponds to time t is equal to 0. That means when the vector was the A was here, then only we started our clock. So therefore, the angle it has traversed will be, and let this angle be phi. Now the x component and y component, this is the x component which is A cosine omega t plus phi, and this component is A so the general representation of a harmonic function of time can be done by taking the projections of a rotating vector. Here the angular speed of this rotating vector whose projections are varying as harmonic functions of time, that corresponds to the circular frequency in radian per second, and each component, and the phase difference phi we can always have by suitably taking our location of the vector with respect to the x and y directions along which we are taking the projections. That angle whatever we select, that gives us this phase phi. Now as I mentioned, let us take a particular example. We will take a very simple example to begin with. So the problem is like this: we have a cantilever beam of length L, and the flexural rigidity, that is the product of its second moment of area of the cross section and the modulus of elasticity of the material EI. At the end of the free end of the cantilever beam, we have placed a block of mass M. We also mentioned that the mass of the cantilever beam at this stage we can ignore compared to the mass of the block at the end. So, therefore, we will treat the cantilever beam as a simple spring element, and it does not possess any inertia. Now, we know in this case the motion is going to be up and down motion of this. So, therefore, we can actually treat this problem with lump parameter model. We can make that the cantilever beam's end, which can move up and down, but it is subjected to some constraint force which is proportional to the deflection and multiplied by the stiffness represented by this. So, therefore, we can represent it by the equivalent spring, massless spring, whose stiffness is simply K equivalent. How much is K equivalent? How to find it out? We take the same actual beam and apply a load, say load F. Then what happens? The beam deflects. And this deflection, let me call delta. So, and if you apply the same force here, it should be deflected by the same amount. So, here the deflection delta is equal to how much? F by K equivalent by definition of a spring stiffness. How much is the deflection of this? Here we know delta is equal to, you know, the flexural rigidity of this is given. So, therefore, it is going to be L cube by P E I. It is from beam theory. For simple cantilever beams, deflection at the free end is given by this. So, sorry. So, therefore, if this has to be replaced by this, the deflections at the end because of same force must be same. So, therefore, we will get K equivalent is equal to so this is modeling, and we have now replaced the actual system by a lump parameter model. Now we have seen the equation of motion. This is the equilibrium position. And we measure x from here. We should remember now our previous analysis and recognize the fact that we do not have to consider gravity anymore, because we are measuring the displacement from the equilibrium which was under the action of gravity. And what is the equation of motion? We all remember it, that m x2 dot is equal to minus K equivalent x, or omega n square is simply that will give you x2 dot plus omega n square x equal to 0, where omega n square is square root of now K equivalent we have already found out. So, this is nothing but and frequency sorry this is not frequency is equal to 1 by 2 pi So, for a cantilever beam, the natural frequency of oscillation when it carries a block of mass m at its free end is given by this quantity. So, if the material is harder, that is E is higher, frequency will be higher. If the system cross section is thicker and I is more, it will again become higher. However, if the length is more, then it slows down and it increases or it decreases at a very fast because if L is large, frequency will decrease and it is proportional to inversely proportional to the L to the power 3 by 2. On the other hand, if m is increased, again the frequency will decrease as square root of m. So, therefore, the most sensitive factor in controlling the frequency of a cantilever beam is its length. So, this is a fairly simple example, but I wanted to tell the steps which normally one has to take. Sometimes we do it very quickly without going in details through the intermediate steps like this. But first thing is developing the mathematical model, lumped parameter model, then framing the equation of motion and then solving the equation. I think in the next lecture we will take up more complicated problems. Particularly, we would also like to take situations where the restoration is by gravity, and we will also try to figure out if there are other approaches of solving such problems, particularly in cases where there is no damping or no dissipation. You have noticed that we are solving the simplest possible that there is no damping. So, in such case the total mechanical energy is conserved, whether we can use that to make use of or that particular condition of conservation of a total energy in solving some problems. We will look into that also in the next lecture.